Okay, welcome back. Today we are going to continue our hunt for Maxwell's equations via differential forms. Excellent exercise. We've already reviewed our notion of differential forms, and now we are going to start exploiting that use to reconstruct Maxwell's equations using those differential forms. So let's begin. So let's begin by taking a quick look at the electric field as we understand it in regular electricity and magnetism physics, meaning our elementary physics expression, our elementary engineering expression. We treat the electric field as a vector in the sense of a little pointy thing that has magnitude and direction. This notion of the word vector, we're changing a lot now, right? We've discussed vectors in various courses on this channel in many different ways, and the least way we've ever discussed vectors is a little pointy object with magnitude and direction. That's the last thing. That's the first thing you know when you come into this class, but it's the last thing we use to actually discuss a vector. Ultimately, we're trying to get away from that idea. But now we're kind of going back to this notion of the vector as you learn in elementary physics. Often this is called in books that discuss this stuff, meaning discuss differential forms, they call this the vector in the sense of Gibbs, which is basically vector analysis as you learned in college and high school even. The Gibbs vector analysis formalism is what we're taught. And that's a totally fine formalism. In fact, it's the one that is by far dominant in the education and the field of this subject. And that's what I mean by this guy right here. We have a component of the electric field in the x direction, and this is its unit vector in the x direction. Component in the y direction, the unit vector in the y direction, unit vector in the z direction, and the component in the z direction. So now we take this notion of the vector, and we're going to start moving it into the more sophisticated versions of things. And what we realize is that our electric field exists on some sort of manifold, right? We have some kind of manifold that has some sort of coordinate system, an x, y, and z Cartesian coordinate system. And now this being a manifold, it's a very simple one, right? It's an x, y, and z spatial manifold only. There's no fourth dimension. There's no time in it yet, right? So with this kind of manifold, it's very easy to say, okay, we can just take this unit vector and immediately translate it into the language of vectors in a tangent space on a manifold. Meaning, what we can now do is we can now say that these unit vectors are actually differential operators that work in the tangent space, and we now presume that we have a tangent space at each point of space in the manifold. And that's how we describe vectors on a manifold. So we've already gone from the elementary notion to this more sophisticated notion. Now, you can do it by direct substitution. You directly take these unit vectors and you just say, okay, we're going to use unit vectors on a manifold, so those are differential operators. So you're almost just doing a symbolic rewrite, right? And that's the first and easiest step. But notice that I was very fond of these subscripts for the x, y, and z in our standard practice, but now I turn them into superscripts in order to be able to exploit ultimately the notion, the Einstein summation convention, E say alpha partial alpha, right? So now we start going to this up-down convention once we make this change into a manifold, a vector field on a manifold. So that's important to keep an eye on. But since we're still talking about regular space and Newtonian physics, really, we note that the inner product on all of these tangent spaces, or the metric, as you will on the manifold, right, is just your standard Euclidean metric, which means that the inner product of partial alpha with partial beta in each tangent space is just delta alpha beta, right? And because of this, the values of E, whether the subscript is up or the subscript is down, is irrelevant. It's not affected by going to the dual space, right? And because of this, because we've chosen this metric, we have a one-to-one correspondence between all the vectors that live in the tangent space and all the forms that live in the cotangent space. So for every electric field vector in our manifold, we have an easy one-to-one correspondence with an electric field covector. And we just simply replace the vector operators, or the unit vectors, with unit differential forms. And this one-to-one correspondence right here between these two is all driven by our choice of the metric. And what's more important is this choice of the metric means that this particular choice of the metric, right, this trivial choice where we have this delta function, it means that these superscripted versions and these subscripted versions are the same, right? Now, had we chosen the metric of Minkowski spacetime, which is a four-dimensional spacetime, right? And we will do this. We would have had an E0 here, but the E0, it would not have been the same. It would have been E0 equals minus E0, right? Because the metric there includes partial zero equals -1. Or sometimes they, depending on your convention, sometimes these guys here are all equal to -1, and this guy equals +1, depending on the convention. The point of this, though, is that the way we're going to look at our Maxwell's equations today in 3 dimensions, or at least right now in 3 dimensions, with a regular standard Euclidean metric, all of this stuff is basically equivalent, right? There's isomorphisms between this vector space and this vector space, and then there's an isomorphism between this vector space and this vector space. These isomorphisms are slightly different in what drives them, right? This is purely a notational thing, right? We're not exploiting the machinery of tangent spaces when we do your regular Gibbsian vector algebra. But as soon as we start talking in terms of manifolds, which is the real mature grown-up way to do this, then yeah, we need these vector operators to tell us that we're dealing with a vector that lives in the tangent space at every point. And then so that transition here is really almost more of just a formalism translation, because in principle this is living in the tangent space as well. It's just we're not concerned. We don't use all the rest of the machinery of differential form, so we just ignore it and we just give it these little letters. It's almost just a purely symbolic change between this and this. But from going from here to here, that's a statement about the metric on the tangent spaces, right? That's a statement about this inner product for each tangent space and the metric on the manifold. And because it's Euclidean, we can make these equivalences. And all of this machinery, all of this up-down index machinery is a bit hidden under the hood because the metric is so trivial. And there are plenty of books that do, in fact, I would say, make things even more confusing by just going ahead and putting the subscripts down here, right? And they'll even put the subscripts on these forms down here. I've seen papers do that because they don't care, because they know the metric is the regular Euclidean metric and none of this really matters. But for what we're talking about right now, I want to make sure that you understand that we can move very freely between these 3 objects in Euclidean space. And actually the way I've done it, you can even move freely between these 2 objects in Minkowski space as long as you keep track of the up or down indices, because the metric will take care of the sign differences in this case. So here we have the electric field as a vector and the electric field as a one form, and this movement between them is completely free. We are allowed to make those changes. All right, so what's next? All right, so I want to go from I want to move away from this for a moment and go back to our quick review that we did in a previous lesson about differential forms and show you that we studied the exterior derivative of a function on a manifold. And we came up with this expression, right? It's the, in this case, I guess, the eta partial derivative of f multiplied by the ethth differential form, and we're ethth elementary differential form or basis differential form, and we did this Einstein sum. What's important to see is if we flush this out, what do we get? Let's do it. We get this very obvious. I mean, I've just blown up all I've done is blown up the Einstein sum, and we get the partial derivative of f with respect to the x-axis, or the first variable, the partial derivative of f with respect to the x2 axis, and partial f with respect to x3. Maybe just to be a little clearer, I'll write it this way so we can see exactly what we're talking about. Remember, this is all shorthand, right? I don't want shorthand to start confusing people, but if you're not remembering, because there's amount of time between these lectures, this and this are the same, right? This is the same as that. So, but when we look at this, right, now when you look at this, we have a one form, right? This is a one form. You can see the one form unit vectors or unit covectors there. And this is a number, right, because we are presuming that this is a one form at a given place in time. Right? As it's written, this is a one form on the manifold because this is a function, right? Remember, f is a function of x1, x2, and x3, which is the equivalent of saying f is a function of x, y, and z in sort of the Gibbsian presentation, but it's the same thing, right? x1 is x, x2 is y, x3 is z. So x is a function, so this turns out to be a function of x1, x2, and x3 as well. So these are functions on the manifold, but multiplied by these unit covectors. So this thing is a one form on the manifold, but at any given place on the manifold, each of these functions takes on a value and suddenly becomes, a real number. And so at each point, you end up with a real number here, a real number here, and a real number here. And ergo, at each point, you end up with a no-kidding covector, which is a scalar real number multiplied by the one-form unit vector. So we have this, we've now created this one form. We've taken the exterior derivative, right? The exterior derivative of a function by this definition that we studied earlier gives us this expression right here. And now we execute our freedom to turn that into a vector, right? So how do we do that? Well, I'm going to take this. I'm going to now simply erase these one forms, right? And I am going to replace them with vectors, right? And now we have a vector living at every point in space-time, because we can do that because of this immediate correspondence between vectors and covectors. And I could go as far as, instead of writing those, I could have written x hat, y hat, and z hat. The point being that when you write it with x hat, y hat, and z hat, your elementary brain should be going, wait a minute, this is simply, this now, as written in a vector form, is simply the gradient, right? That is literally the definition of the gradient of a function as we've learned from vector calculus, right? So the point is that the gradient of a function is very tightly connected to the exterior derivative of a function. In fact, they're entirely equivalent, right? And that exploitation is pretty important because we're going to now start doing that kind of thing, connecting Gibbsian notions to differential form notions for everything we do. before I move on, I do need to point out, this is not an equality, right? I did not write gradient function equals the differential form or the exterior derivative of a function, because it literally isn't, right? You've got this issue of you end up with a form on this side, and this is our vector notion. So I went with this symbol, something like, I guess, an arrow. Like you can replace the gradient with the differential with the exterior derivative, understanding that we have to always track between these isomorphisms between forms and vectors and this Gibbsian unit vector idea, right? So the gradient of a function is tightly bound to its being a differential operator. And in fact, you can see the coefficients are the same. They all have unit vectors. So you can make these replacements. This is an important replacement we're going to probably be exploiting in order to write our Maxwell's equations in the language of differential operators. Because there's a lot of gradients in Maxwell's equations, right? But they're not gradients of scalar functions. They're gradients of vector fields. So we still have a little work to do. But this is a start. So let's go to the next step here. All right, so now we are going to study this notion of the divergence of a vector field. So the way this is written here, of course, is the standard electricity and magnetism first year course vector analysis expression for the divergence of a vector field E. So those standard vector fields I'm going to write with a little arrow on top. When I say standard, I mean the Gibbsian vector analysis vector field. So that's what this is. And this is the divergence, right? So the divergence is expressed in those in the basic Gibbsian form as follows, right? If I wrote it in just the straight up way that everybody's used to seeing it, this is this gradient operator. It's a gradient vector field, right? But it's got these differential operators for components, right? And so the divergence of a vector field is given by this simple expression when the vector field we're talking about is the electric vector field expressed in this form here. So what we're going to do is we're going to see how we can translate this into the language of differential forms. And we're going to do this sort of stepwise. It's motivated by how it ends, so we'll just do it sort of step by step, and we'll see that we land in the right place. So for example, first thing I'm going to do is I'm going to translate this electric vector field of standard classical mechanics into the differential forms version, right? And that is a free movement, right? So all of a sudden, this object now is moved from this form here, right? The Gibbsian form. We're just immediately dropping it off into the one form. I shouldn't say Gibbsian form. I don't want to use that word, right? So I want to say the language of Gibbs, or the language of standard vector calculus, to the language of one forms. And this movement is absolutely free. So that's the first step we do. And then we are going to find its Hodge dual, right? And we know how to do the Hodge dual because we did that in the entire last lecture, right? So we know the Hodge dual is linear over the coefficients of the one form. So we pull out this E1 and E2 and E3, and we're now looking at the Hodge dual of the basis vectors, which we calculated last time, right? We calculated last time that the Hodge dual of dx1 was dx2 dx3. The Hodge dual of dx2 is minus dx1 dx3. Now I could have switched this to dx3 dx1 and put a plus sign there, but for whatever reason I chose not to do that. I think it's because it works out without it. And the Hodge dual of dx3 is dx1 dx2. So with all that in place, we now have calculated the Hodge dual of the electric field. We have E1 dx2 dx3 minus E2 dx1 dx3 plus E3 dx1 wedge dx2. And notice the Hodge dual of a one form, right? That's what this is. This is a one form. The electric field is a one form. The Hodge dual of a one form in three-dimensional space, right, is 3 minus 1 equals 2. It's a two form, right? And sure enough, these are two forms. And we did all those calculations to go from here to here in the previous lecture, right? So you should be comfortable with that. It was totally not trivial, right? Because we had to figure out what this sign was, and sometimes the sign throws you for a loop, and you end up with a minus sign there. But where you don't develop a sign in three-dimensional Euclidean space is you don't develop a sign because of the inner product having a -1 in its signature. You don't have that in three-dimensional space. You do in 4, but not in 3. So right now we have calculated the Hodge dual of the electric field. So our next step is to calculate the exterior derivative of the Hodge dual of the electric field. So let's now do that. So to calculate this exterior derivative, I'm going to use the formula and method that we talked about in the previous lectures. It comes down to this. It comes down to finding this sum, this one form sum of the components, right? You form a one form of the components, and then you wedge it with the two form basis vectors. Actually, now that I'm looking at this, there should be a wedge here. There should be a wedge in each of these things, right? Because ultimately, remember the differential form. The reason I can tell right away is not the differential form. The exterior derivative is always one form higher than the form that you're taking. So we have the exterior derivative of a two form has to be a three form. So here we have two form basis vectors that we're summing over, because we're summing over a collective index, and the collective index is 2, 3, 1, 3, and 1, 2. And but the answer has to be a three form. So this is a one form. You can't just have a one form multiplied by a two form. You need to express what kind of multiplication you're dealing with. And we're dealing with wedge multiplication. The formula we're using is this formula over here. Where was it? Right here. It's these two formulas, right? Alpha is a K form with this collective index I, right? And let me erase this so it's not so confusing. Alpha is a K form with the collective index I, and the exterior derivative of alpha is this sum over these partial derivatives of the component, right? And the component is a function on the manifold, so these partial derivatives make sense. But it's a one form, right? It's essentially using this definition here, right? This definition, we're taking the exterior derivative of a zero form. That's what's happening here. You're taking the exterior derivative of the zero form alpha I, and that gives you a one form, and you're wedging that one form into the collective index. So we exercised this a couple lessons ago, but just as a reminder of where this came from. And voila, that's what we're doing here. We're actually blowing it up. So now we have found the exterior derivative of the Hodge dual of the electric field one form, and that's what this thing is. But what you see here is you have dx3, dx2, dx3, for example. So that one is 0 because you have a condition where you have the wedge of dx3 with itself. So that term goes away. But this term survives, and this term survives. This term goes away too, right? Because now you have dx2 wedge dx2 dx3. So that term goes away because you have two dx2s being wedged together. So the only term that survives is partial 1 e1 dx1, and this becomes dx1 dx wedge dx2 wedge dx3. So that's the one surviving three form. So this one's gone and this one's gone. And in this case, this one's gone and this one's gone. And in this last case, that one lives. These two are gone. But in every case, there's the resulting three form. They're all the same. The three form space in three-dimensional space is one dimension, right? In other words, there's only one three form. It's dx1, dx2, dx3. So we shuffle these around, and every interchange introduces a minus sign. But in the end, what do you get? Well, in the end, you get partial 1 dx1, dx1, dx2, x3, minus partial 2 dx2, dx2, dx1, dx3, partial 3 e3, dx3, dx1, dx2. Did I say that right? Partial 1 e1, dx1 wedge, dx2, dx3, for example. And then you can combine these all together by shuffling, by flipping dx1, dx2, and you lose the minus sign. And here you flip dx1, dx3, and then dx2 and dx3, and that's two minus signs, so you don't change that sign at all. And what do you end up with? You end up with partial 1 e1 plus partial 2 e2 plus partial 3 e3 multiplied by what? This 3 form, this single 3 form. And now we start realizing, well, look, the coefficient of this looks a lot like the Gibbsian definition of the divergence. So the Gibbsian definition of the divergence lands as the coefficient of the 3 form that results by taking the exterior derivative of the Hodge dual of the electric field. But that's not what we want. If we're interested in just purely extracting the divergence, what do we have to do now? Well, we have to get rid of this thing. Well, that's easy. We just take the Hodge dual of this object, and then that takes the 3 form and gives you a 3 minus 3 form, which is a 0 form. So we're now interested in the Hodge dual of the exterior derivative of the Hodge dual of the electric one-form field, and what do we end up with? We end up with something that exactly equals the divergence of the Gibbsian vector field E. I guess I'll do that. And that is an equality. Phew. So that's really interesting. So now we know how to write down the divergence of a 3 form, right? This is the 3 form. The divergence of a 3 form is the Hodge dual of the exterior derivative of the Hodge dual of that 3 form. And that ends up being the divergence. And you can see what we're going to do with this, right? I mean, ultimately, Maxwell's equations, there's a divergence, right? This first one is the divergence of the electric field. This is literally what we want. And here's the divergence of the magnetic field, which written in Gibbs's language is written this way. And so you can almost immediately see that this equation is clearly going to be, it's going to be the Hodge dual of the differential of the exterior derivative of the Hodge dual of B equals 0. And now this equation, at least, is written in the language of differential forms, right there. But we'll get to that. We'll get to that a little more thoroughly when we actually do this. Right now, we have to understand how do we interpret these Gibbsian expressions in terms of differential forms. And so far, we've figured out 2, right? We figured out we figured out only 1, the divergence, right? Actually, all of these little divergences here, to be true with sort of the Gibbsian language, should be written down as vectors, right? So let me do that real quick. Okay, so now we know the divergence of a 1 form is given by this expression here. So now let's have a look at a different process. We're now going to look for the curl. Let's have a look at that. So again, with the curl, we start with the Gibbsian form of the electric field. Now, of the magnetic field, in this case. We could do this. We could ask for the curl of the electric field. I'm just choosing to exemplify this with the magnetic field because we've already just done the electric field. What's an interesting thing to understand here is that this vector form of the magnetic field, which we'll immediately write in this form right here, in this language, the language of the manifold. In other words, I'm skipping, well, actually, I guess that's true. If I'm going to skip the Gibbsian form altogether, I'm just going to write B is this vector field on the manifold, right? It's exactly analogous to what we did up here with E, right? With E being, we're just going to start right here. We're skipping this step now. So we're starting right away with B being a vector field on the manifold, the magnetic field on the manifold. Now remember, you may remember that there's axial and polar vectors in electromagnetism. So we're still kind of stuck with that right now because this is just really a regular vector. But we know the property of magnetic fields is such that it behaves as it's an axial vector, right? Hold on. So there's two words, right? There's axial and a polar vector in the Gibbsian world, right? In the Gibbsian world, you have axial vectors and polar vectors. And the magnetic field is an axial vector, or the electric field is a polar vector, right? So electric fields are polar, magnetic fields are axial. So you have these two different kinds of vectors in the Gibbsian world, right? And a lot of what we're going to be discussing here kind of attacks that and tries to create there's only one kind of vector, and we want to sort of understand what's under the hood with this axial and polar vector thing going on, right? And a lot of what I've been reading about lately is a form of electromagnetism called based in this notion of something called geometric algebra, which completely eliminates this notion of axial and polar vector, which is fascinating. But right now we're just dealing with the magnetic field as a vector field, understanding that it is an axial vector field. So this is also called a pseudo vector because of its behavior under reflections. But with that aside, let's not worry about it. Right now we're just going to treat it as a vector field, and we're immediately going to look at it in its one-form version. And then instead of remember what we did up here in this example, the first thing we did is we took the Hodge dual right away. Now, instead of doing that, let's take the exterior derivative right away. And the exterior derivative of a one form is very easy to calculate. This is the formula for it, basically. It's these partial derivatives of the component fields, and it's just wedged right into each of these forms, each of the components of the field itself, and it ends up being a two-form, which of course is correct, right? If we treat the magnetic field as a one-form field, which is totally free, the exterior derivative of a one-form field is a two-form field defined this way. So we blow this guy up, and when we blow it up, meaning executing the two implied sums, we end up with all of these 9 terms, partial of x1 with the first component of the magnetic field, dx1 wedge dx1, which that's going to be 0, right? Because dx1 wedge dx1 is going to go away. So we know that that'll be 0. Likewise, the dx2 part will be 0, dx3 will be 0. And then that just leaves us with these components here. And what you see is you have the second partial derivative of bx1, dx2, dx1, and then you find the first partial derivative of bx2, dx1, dx2. And the only difference between these two, well, the components are different, right? But between the basis vectors, it's just a sign change, right? You flip these two, you get a minus sign, and you can add them together because they have the same basis vector, the same two-form basis vector. And so that allows you to take these 3 and compress it down, or these 9, you eliminate the ones that are 0, and you combine, so that's 9 minus 3, that leaves you with 6. And of the 6, they pair up with a minus sign between them, and that's what gives us this expression right here. And so now we're looking right here at this expression, and it doesn't take too much squinting to see that this is beginning to look like the components of the curl of a vector field. Now, the curl of a vector field is another vector field, so we have the components that match up the curl, but the unit vectors are actually two forms. So this is a two form whose components actually exactly match the curl of a vector field B, right? So, in other words, if this was if this was, let's see, what would it have to be? This would have to be x3 hat, and this would be x2 hat, and this would be x1 hat, right? If that's the way it was, then that would be exactly the curl of the vector field B, written with these components in blue. But that's not what we have, right? What we have is a two form whose components happen to match that of a curl. So if we want to extract the curl, we have to convert these two forms back into one forms, and then the one forms we would convert back into vectors. So now, but we know how to do this. Well, so we have a tool to convert a two form into a one form. Now, we're not certain that that tool will do what we want, but let's give it a try. So now we take the Hodge dual of the exterior derivative of the one form field B, and we end up with this expression. The Hodge dual of dx1 dx2 is dx3. The Hodge dual of dx1 dx3 is minus dx2. And the Hodge dual of dx2 dx3 is dx1. So we have this minus dx2 in there, but what we're going to do is we just flip the order in here, and when we flip the order in here, and we just write down, what is the curl of a B field? Well, that is what the curl is, right? This is the definition of the curl of the magnetic field, where we're using our manifold form for the unit vectors, but we have free movement between dx3 and partial 3, dx2 and partial 2, and dx1 and partial 1. That's free. We're allowed to do that change in Euclidean three-dimensional space. And this minus sign is taken care of by flipping these two around, and this is exactly what the curl equals. Phew. So now we have an expression for the curl of a vector field in the Gibbsian sense is the Hodge dual of the exterior derivative of the equivalent form field. And so now we can express curls and we can express divergences for one forms. Okay, well that's kind of nice. So let's take a look at how we might exploit this. And I just wrote in a few very quick little lines here, but say we were interested in the curl of the gradient of a function. Well, we now know that we can take the gradient of a function and substitute its exterior derivative. That's a substitution where we discovered we could make very early on. And now we just learned that the curl of a function is the curl of a one form, right? This here ends up being a one form, right? Because the gradient, because the exterior derivative of a zero form is a one form. But now we want the curl of a one form, right? That's what this whole expression is. It's the curl of a one form. And we just learned that the curl of a one form is the Hodge dual of the exterior derivative of a one form. So we're now going to take the Hodge dual of the exterior derivative of this one form, which is the equivalent of the Hodge dual of the double exterior derivative of a function. But the double exterior derivative of anything is zero. So we immediately can see that the curl of the gradient equals zero right away, right? That proof becomes super trivial, right? The proof that the curl of a gradient is zero is now become a one-liner. And that's an important idea. Not that the curl of the gradient is zero. That, of course, is an important idea, right? This this theorem is an important idea, that the curl of a gradient field is zero. Or I should say the curl of a vector field that is the gradient of a vector field which is defined as the gradient of some scalar function, that is zero is very important. It's not trivial, but this proof suddenly becomes trivial once you use the language of differential forms. And the reason that's important is because, and I'm very guilty of this, and if we discuss geometric algebra, you'll see me talking about this a lot probably. I'm wondering, is this all just bookkeeping, right? Is this underlying stuff really simplifying things, or is this just all fancy bookkeeping? And I think one of the arguments against this being just fancy bookkeeping, instead of a battle between the Gibbsian notation and the differential forms notation, and to say, no, the differential form notation has an underlying fundamental quality to it that goes beyond just notation. There's actually, it's a better way of looking at the way that nature works. One of the hints that you're onto something is when complicated proofs become really simple. And when complicated proofs become really simple, you know that you're probably dealing with something that has some fundamental information embedded in it. That means there is material in here that does not exist in this form. So the Gibbsian form simply doesn't have a certain amount of information. And that's kind of why I talked about the axial and polar vectors. In the Gibbs world, you have a vector and you have to give it a label. Is it a vector or is it a pseudo-vector? Right? You have to decide. And every vector you have to say, oh, here's a vector in three-dimensional space. Oh, this one is a polar vector, but this one here is an axial vector, right? And you have to track that, right? You have to somehow remember. But what we're going to discover is that's not the case with differential forms. With differential forms, you can escape the notion of axial and polar vector. What you really realize is that polar vectors are one forms and axial vectors are actually better expressed as two forms, right? Two forms. And that's where the minus sign, when you flip or reflect in the mirror in two forms, minus signs start generating naturally when you do these flips. And so you don't have to articulate that, oh, don't forget to add the minus sign if you flip the coordinate system. It's actually part of the design of a two form that it will change sign. We'll discuss that more later, but right now, what we have learned is that the divergence of a one form, we've learned how to calculate the divergence of a one form, and we've learned how to calculate the curl of a one form. And now we need to learn how to do the divergence and curl of two forms. Before we go on, though, let me do another quick proof here. How about the divergence of a curl? We know that the divergence of a curl is always going to be zero. Well, okay, so we treat A is a vector field in Gibbsian form. So in the Gibbsian language, A is a vector field. So we're going to turn A into a one-form field. And we know that the curl of a one-form field is the Hodge dual of the exterior derivative of the one form. And we know that the divergence is the Hodge dual of the exterior derivative of the Hodge dual of a one form. So this is going to be a one form. And this is the Hodge dual of a one form, which will be a two form. This will be the exterior derivative of a two form, which will be a three form. And this will be the Hodge dual of that three form. So the Hodge dual of a Hodge dual, right, that is, we un-Hodge dual it, so that just goes away. So we end up with the Hodge dual of the exterior derivative of A. And for the same reason, the exterior derivative of an exterior derivative is always zero. Kaboom. So we've proved this with one little line, one little tiny line. So that really makes me feel like, wow, this is actually really big news, and it's an important adjustment in our way of thinking, getting out of the vector notation of E and M into this form notation. That's got to be worth something. Okay, so what next? So next we need to do this process for two forms. And what we're going to learn is that the divergence of a one form has the same structure as the curl of a two form. The curl of a one form has the same structure as the divergence of a two form. And then we're going to see how we can translate Maxwell's equations into form equations. And we will do that next time. All right, so I'll see you next time.